Chapter 10, the material we're supposed to go over on Wednesday, is all about probability. A probability experiment is a process which leads to well-defined results called outcomes. You'll notice this term, well-defined, we also used in sets. So this is on purpose because everything we do in probability can be thought of just like a set. So a lot of our notation that we learned in sets is going to come over to probability as well. So an example of a probability experiment is flipping a coin. So that would be a well-defined um, probability experiment because we have there are outcomes that we can get and we know what those outcomes are. So we have predetermined what heads is and what tails is. If you were flipping a coin that didn't have different things for each side, then that would not be a well-defined probability experiment. So then the outcome of this would be flipping a coin and getting heads. So that's one possible outcome. The other outcome would be flipping a coin and getting tails, because there are only two outcomes that we have for this probability experiments. A sample space is the set of all possible outcomes of a probability experiment. So notice that we use the words it's a set. So these are going to be sets. An example of flipping a coin. The sample space would be the set of either heads or tails. So these are all the possible things that you can get from doing this probability experiment. Another example would be rolling one die. I always mix up which one's the plural or the singular, so I apologize if I use the wrong one there. So rolling a die, you could get a 1, 2, 3, 4, 5, or 6. And so there are 6 things in the set of all possible outcomes of rolling one die, so that's our sample space. Um, we always assume it's a 6-sided die unless told otherwise. So yes, there are different levels of die like D20s or things like that, but we assume 6-sided die unless otherwise told. One more example would be answering a true-false question. So the sample space of that would be true and false. There are only 2 possible outcomes to answering a true-false question. An event is any subset of the sample space. So as an example, let's say we have the experiment that is drawing a card, and we're going to say this is a standard 52 card deck. We'll go over what's in a 52 card deck in just a little bit. So the sample space is going to be the set of 52 cards. And then an example of an event might be drawing an ace. The event is just something that we're doing that gives us an outcome, which is one of our 52 card things. And in this class, we're only going to be doing drawing one thing or doing one thing. We're not going to do more than that. So it's going to be pretty simple in the case of this class, but it can get more complicated with events that, like when you're doing multiple events in a row or things like that. So we have two different types of probability. There's experimental probability and theoretical probability. So experimental probability is, let's say we roll a die 7 times and we get a 4 3 of the times. The probability, then the experimental probability of rolling a 4 would be 3 out of 7. That's not the same as theoretical probability, though. Theoretical probability talks about if I were to do this an infinite number of times, basically, what is the likely outcome that I would get for this? How many times would I likely to be to get that outcome? So we're just going to talk about theoretical probability in this class. So formally, we call this the probability of an event E occurring. So the probability of E, you'll notice that we use this just like our set notation. If I wanted to find the cardinality, the number of items in a set E, I would write it like this. So it's just the same, we're just talking about probability this time. So the probability of an event happening is the size, the cardinality of the event over the size of the sample space. And so you want to think of this, the event is the number of ways what you want can happen. And then S is the total, all the total possible outcomes. So where S is the sample space. And then in this class, again, we're going to be assuming every outcome is equally likely. It gets more complicated if you allow some things to be more likely than others. Oh, sorry, I wrote down the wrong thing. So when we think of probability, what you want to remember is that it's the number of ways what you want can happen over the number of ways anything can happen. And this is what you want to keep in mind when you're doing your homework. So let's see some examples. A die is rolled. What is the probability of rolling the following? So before I ask you the questions, let's figure out our sample space. So a die is rolled, which means we assume it's a six-sided die. So we get 1, 2, 3, 4, 5, 6 is going to be our sample space. And you can also note that the size of S, we have 6 elements in it, so the size of S is going to be 6. So once we know that, we want to find the probability of rolling a 3. We think number of ways what we want can happen. There's only 1 3 in this whole sample space. So the number of ways what we want can happen is going to be 1, and then the number of ways anything can happen is going to be 6. So your probability is 1/6. So you want to think the event is just the 3, and then the sample space is what we saw above. And so then the size of the event is 1, and the size of the sample space is 6, so we get 1/6. So what about an a number less than 5? So the number of ways we can roll something less than 5, that's going to be all the numbers 1, 2, 3, and 4, not including 5 and 6 because those are not less than 5. So then the size of E is there are 4 things in it. So you get 4/6, which reduces to 2/3. And C would be that we roll an odd number. So the set of all odd numbers, the way we can roll anything, the way we can roll what we want to happen is 1, 3, and 5. So the size of our event is 3, which means we get 3/6. So your probability is 1/2. So it's pretty straightforward when you just think the number of ways what you want can happen over the number of ways anything can happen. Let's go over some facts about probability before we do another example. So first, probability is never negative. Meaning you can never have a probability less than 0. So this should make sense. 0% chance of something happening means it's not going to happen. We can't have like the opposite of that going like the opposite will happen or something like that. It's just 0 is the absolute bottom. The second is probability is never greater than 1. And when we think one, if you were to convert that to a percent, that would be probability is always smaller than or equal to 100%. So this is where you guys have probably heard you can never have a percent over 100 and then maybe have gotten confused because we see percents over 100 all the time. When they say you can't have a percent over 100, they're talking about probability. You cannot have more than a 100% chance that something is um, going to happen. And 100% as a decimal is 1.00 because you just move your decimal point back twice. So that's why probability can never be greater than 1. The third fact is when an event can't occur, the probability is 0. And when it's certain, the probability is 1. Does that make sense? You have 0% chance when it's not going to occur. You have a 100% chance when it is going to occur. And then the last one, if you add all the probabilities for every outcome in the sample space, the result is always 1. Basically, there is a 100% chance that anything can happen. So when you say it in those words, it should make sense. If we take the sample space of rolling a die, then there's a 1/6 chance that we roll a 1, a 1/6 chance that we roll a 2, 1/6 chance that we roll a 3, etc. And if we add them all together, 6/6 makes 1. And that's going to be true for any probability. It can't be a probability if that's not the case. And because of this, we also get another rule that we have, and that is the probability of a complement. So complement means the same thing in probability as it does in sets. So E complement is going to be E not occurring. So for any event E, if E complement is the event does not occur, so just like in sets, we put the word not in front of it, then the probability of an event not occurring is 1 minus the probability of the event occurring. So if we go back to this set of the sample space of rolling a die, let's say we roll an odd number, then the probability of rolling an odd, so I'm going to say E is 1, 3, and 5. Then the probability of not rolling an odd is 1 minus the probability of rolling an odd. So we did that above. We got that the probability of rolling an odd number is 1/2. So then we get 1 minus 1/2 is 1/2. So the probability of rolling not an odd number, aka the probability of rolling an even number, is also 1/2. So rather than counting how many ways you can have what can occur, you could instead use the complement and a lot of the time count less. Let's see an example on this. Of the next 32 trials in a court, 5 are homicides, 12 are drug offenses, 6 are assaults, and 9 are property crimes. If jurors are assigned to trials at random, what is the probability a juror won't get a homicide case? So one way to do this is to add up everything that's not a homicide case. That's the number of ways what you want can happen over the total number of ways anything can happen. But let's practice using our complement rule. So if we make the probability of getting a homicide, there are 5 homicide cases, so that's going to be 5 over 32 total cases. So then if we want to find the probability of not getting a homicide case, we take 1 minus the probability of getting a homicide case. And that gives us 1 minus 5 over 32, which is 27 over 32. And so that's a little bit easier than adding up everything else together, which would give you 27 over 32. So one more problem I just want to go over for those of you who don't know what's in a standard 52 card deck. So you draw a card from a standard 52 card deck. What is the probability that you draw? And then I'm going to list the things that I want you to find, but first let's go over a standard 52 card deck. So in a 52 card deck, we have 4 suits. There's hearts and diamonds, which are red. So I'm going to write those in red. And then clubs and spades, which are black. And because my screen is black, I'm going to use white for those. And then for each of these, we have ace, and then the numbers 2 through 10. And then a jack, a queen, and a king. And this is going to be true for all of them. Let me see if I can copy and paste this to save some time. Use use my keyboard real quick. So we have all of that for heart and diamond. Let's see. Can I change the color? Can't change the color, so I'm just going to rewrite them again once in white. And then I'll copy and paste them. And this is what a standard 52 card deck consists of. So the letters, Jack, Queen, and King, are what we call face cards because when you're looking at a standard deck of cards, they have faces on them. So Jack, a Queen, and a King will be like dudes and girls on the page, on the card. So you don't need to memorize this. Alex will give you this same picture that I just drew basically. But you do need to answer questions like, what is the probability that you draw a face card? So we want the number of ways what we want can happen. So there are 12 face cards, 3 in each suit, divided by the number of ways anything can happen, and there are 52 total cards. And you can reduce that to 3 over 13 by dividing both by 4. B is going to be a black card. So we need to count up all the black cards. Because there's 52 total cards and there's only 2 colors, half of them are going to be black. So you could just say your probability is 1/2, but let's go ahead and do this formally. So half of 52 is 26 ways we can draw a black card over 52, and that's going to reduce to 1/2. C is a face or a black card. And I want to include this one because a lot of people will tend to just go ahead and combine these two here, but that would be incorrect because we have some overlap. So here's the face cards and here's the black cards. And if you just added these together, all of these 6 right here would get double counted. So you need to actually figure out how many face or black cards there are. So you can count up everything in this L shape here. So that's going to be 26 for these, plus another 6 gives you 32 face or black cards out of a 52 total possible cards, which when you reduce that gives you 8 over 13. And finally, the last one is going to be um, a not a number card. So one way you can do that is we're going to count up all the cards which are not numbered cards. So you can see that one's pretty easy to do. You're just going to have the 12 plus 4 is 16. However, I want to practice using the complement rule. So not a number card is going to be 1 minus getting a number card. And so probability of not number equals 1 minus the probability of number. And we have the numbers 2 through 10. So that's going to give us 9 numbers. In each suit is 9 times 4 is 36. So we get 1 minus 36 over 52. Which when we reduce that gives us 1 minus 9 over 13. That should make sense because we had 9 in each suit. And then to simplify this, we're going to change the 1 into 13 over 13. And so that's going to give us 4 over 13. And that's the probability of getting a non-number card.